Yes, sir.
Sir, we will wait for 2 minutes.
Okay, we will wait for 2 minutes. Okay. Okay, now we can start. Okay, student. In the previous class, we have discussed about some greedy techniques, greedy algorithms. We have talked about what is greedy algorithm, what is greedy technique. Then we have discussed about some applications of your greedy techniques that were your knapsack problem, that is also called your 0-1 knapsack problem, and job scheduling algorithm and Huffman coding algorithms. Okay, today we will discuss about graph techniques, some algorithms related to your graphs that are also based on your greedy techniques, but in yours, according to your syllabus, they are defined in the next topics or our next unit, that is your graph techniques. Okay, can anyone tell me about graph? Any definition of graph? What do you mean by graph?
It is a collection of edges and
Oh, it is a collection of edges and
edges and
what is edge?
vertices. Yes.
Okay. I have shared a screen to you. Is it visible? I think now it is visible.
Yes, sir.
Yes,
Yes,
sir.
yes, it
It is
is visible.
visible, but a little bit small.
In this class, we will discuss about some basic chronology of your graphs and some algorithms of your graphs, that is your Prim's algorithms, Kruskal algorithms, and Dijestra's algorithms. At first, we will discuss about what is graph, what are the components of graph, some basic of graph, some basics of graph. It is very important to understand the different algorithms of your greedy techniques or your graph. So, what is graph? Graph is a non-linear data structure. Data structure is your how the data is organized in the memory, in the storage, so that we can access it in a more efficient way. That's a structure. So graph is a non-linear data structure that consists of your edges or vertices. Okay. In the graph, you can see that it consists of some arrows and some circle-like structure. Okay. These circle-like structure in which 1, 2, 3, 4, 5 is written, that is called your vertices. Vertices of the graph, and the lines which are connecting these numbers or these nodes, these are called your edges of the graph. So these circle-like structure, these are called your nodes or vertices of the graph, And the connection between these two nodes, or these lines, these are called your edges of the graph. Okay. So vertices are the fundamental unit of the graph. That is also called your nodes. Sometimes every node has a weight to connect with another nodes. The graphs may be either you are directed or undirected. If there is a direction, that is a direction given in the edge, then it is called directed graph. Otherwise, it is called your undirected graph. In the figure, it is the undirected graph because there is no direction from one node to another node. So this is an undirected graph. So these are the components of the vertices. Vertices are the fundamental units of graph. It is also known as the nodes of the graph. Or each node, it's labeled or unlabeled. Either it consists of your weight or not, and not weight. Edges are the connection of the nodes, in which we connect two nodes through the edge. Okay. So edges is just a connection. Edges can also be labeled or unlabeled. Each edges may have some weight, or it can be normal edges also. Okay. So graphs are used in solve many real life examples, as you can say that, to represent your networks. Suppose you are traveling from one location to another locations in a Google map. You can also use some graphs. Also used in social networks like your LinkedIn, Facebook. Okay, each person is a with vertex. So networks in the where you can use network, there then you use the different types of graph. Now the important thing, which is your spanning tree. Okay, that is important for your syllabus, spanning tree, because we will discuss about the spanning tree in all the algorithms. Okay, what is spanning tree? Spanning tree. So spanning tree is a subgraph or undirected connected graph which covers your all vertices, in the spanning tree. We cover all the vertex, all the nodes of the graph with the least possible number of edges. With the minimum number of edges, we want to traverse a complete graph. We want to traverse all the nodes in the minimum spanning tree, in the spanning tree. If any vertex is missed, then it is not a spanning tree. So in a spanning tree, you have to cover all the vertices, all the nodes. So a spanning tree is a subset of the graph that does not have any cycles, because there should be one and only one edges between two edges in the spanning tree. Sometimes it is frequently asked in the interview questions or in many competitive examination that a spanning tree is a subset of the graph that does not have cycle. It is a true statement or not? So it is very important that spanning tree is a subset of the graph that does not have any cycles. And it also cannot be disconnected, because it will cover your all the vertex, all the edges of the graph. If it does not cover any vertex, then it is not a spanning tree. Okay, so that is your spanning tree. So a spanning tree consists of your n minus. If a spanning tree has total n vertices, it must have your n minus 1 edges. Okay, where n is your number. Okay, in the spanning tree, every node and every edge connected with these two nodes must have any weights. Okay, and this statement is very important. The number of edges in the spanning tree would be equal to the number of vertices in the given graph minus 1. as I have told you that the number of edges in the spanning tree, that would be equal to the number of vertices in the given graph minus 1, n minus 1. That's n minus 1 edges. Must have your n minus 1 edges. If there is more than n minus 1 edges, then there must be a cycle in the graph. Then there will be a cycle in the graph. If there is a cycle in the graph, then that graph is not called your spanning tree. If there is a cycle in the graph, then that is not a spanning tree. A spanning tree doesn't have any cycle. Okay. Suppose, for example, a complete undirected graph n into n minus 1 by 2 number of spanning tree. If the value of n is 5, then maximum possible spanning tree will be your 125. If there are total 5 number of vertices in the graph, then maximum possible spanning tree will be your n to the power n minus 2. That will be your 125. Okay. This is example. Suppose 1, 2, 3, 4, 5. These are the vertices of the graph, and this is a weight associated with the edges connected to these vertices. These are the edges, and this is a graph. So how many spanning tree may be possible with this graph? In the spanning tree, there must be all the 5 vertices. Okay, and there must be n minus 1 edges. There are total 1, 2, 3, 4, 5, 5 edges and 5 vertices. So the possible graph may be this type of. You can see that in the spanning tree there are, in all the spanning tree we have 5 vertices. We have 5 vertices and 4 edges, n minus 1 edges. If there is a connection between A and C, then that will be cycle. If A and B, that will also be cycle. If B and D, that will also cycle. If that is a cycle in the graph, that tree or that graph cannot be called your spanning tree. Next is your minimum spanning tree. Because in the algorithm, we will find out the minimum spanning tree. Minimum spanning tree is the one of the spanning tree in which the sum of all the weighted associated with these edges, that will be minimum. If the cost of a complete spanning tree is minimum, then that spanning tree will be called your minimum spanning tree. In all the possible all the possible spanning tree, there will be one graph, one spanning tree, that cost will be minimum. That graph is called your minimum spanning tree. The weight of the spanning tree of the sum of the weighted given in the edges of the spanning tree. So the total summation of all the edges associated with these vertices, that will be minimum. So the cost of that spanning tree will be minimum. If the cost of that spanning tree is minimum, then that spanning tree is called your minimum spanning tree. So spanning tree is a subgraph of a graph which will cover your all the vertex, which will cover your all the node. But in the spanning tree, there must be n minus 1 edges. N minus 1 edges. Okay, the edges will be less than the number of vertices. And in the minimum spanning tree is among the one of the spanning tree in which the cost of that spanning tree is minimum. Okay, if the cost is minimum, then that is your minimum spanning tree. Is it clear? These are the basics of a graph and minimum spanning tree or spanning tree. Okay, this is the basic of the graph. Now we will discuss about the Prim's algorithm. Is there any question regarding this graph, spanning tree, or minimum spanning tree? Okay. Next, we will. Yes, tell me.
So, if you please just tell us about minimum inventory once again. I think it's a bit difficult.
Okay. This is a graph. Okay. For with the help of example, I will try to explain. This is a graph. This graph have, suppose this graph have these three spanning tree. Spanning tree is a part of graph. Spanning tree is a part of graph which will cover all the nodes, A, B, C, all the nodes, and there must not be any cycle. Okay, in all these three spanning tree, one cost is also associated with these edges. If the cost of any spanning tree is minimum, then that spanning tree is called your minimum spanning tree. For example, this is a graph in which there is a cost from 1 to 2, that is 1. There is also a cost 3, 5 to 4 is 2, 2 to 3 is 4, 3 to 4 is 5. Now, I want a spanning tree which is covered with all the vertices. For example, in this tree, what is the minimum is? Minimum weight is 1. Okay, minimum weight is 1. I have selected this route at first. At first, in the first time, I have selected this route 1 to 2 because the cost is minimum. Next, I have selected one more route, that is 4 to 5, that is next minimum. And then I have selected 1 to 5, that is next minimum. Okay, then next minimum is 2 to 3, that is 4. I have selected these edges 1, 3, 2, and 4. I have excluded this one. Okay, so the cost of I have this spanning tree in which I have excluded this edge, the cost will be 4 plus 1 plus 3 plus 2. That will be your 10. That cost will be 10. Now, that spanning tree in all these in which I have excluded this edge and I have covered all these 5 vertices. The cost of that tree is 10 because that is the minimum cost, because I have selected the minimum edges, minimum width of the edges, and the cost is minimum, that is your 10. Now that is called your minimum spanning trees. So in this example, I have selected 1 and 2, 1s, 1 and 5, 1s, 4 to 5, 1s, and 2 to 3, 1s. I have selected these 4 edges and I have covered all the 5 vertices. Okay, then that tree is called your minimum spanning tree. So in all the spanning tree which have minimum cost, that spanning tree is called your minimum spanning tree. Okay, with the help of one Prim's algorithm example, you will understand more clear. Okay.
Okay. Thank you, sir.
Okay. Now next is your Prim's algorithm. Prim's algorithm, it is a greedy algorithm, okay, in which we find out a minimum spanning tree. Okay, in which we find the goal of the algorithm is to find out the minimum spanning tree from a given graph. Okay, so in this algorithm, we start with a empty spanning tree, we start with a vertex, with a source, and we find out a minimum spanning tree of the graph. Okay, so this algorithm finds the subset of the edges. That includes your every vertex, every edge of the graph. And the sum of the weight of all the edges can be your minimized. So this algorithm is to find out the minimum cost of the algorithm. So Prim's algorithm starts with a single node and explores your all the adjacent nodes with all the connecting edges with each node. Okay. With the help of example, we will discuss it. I am sharing a screen. I have shared a screen. Okay. Suppose, for example, there is a graph. I am drawing a graph. Okay. This is a graph with total 5 number of vertices. This is not your directed graph because there is not any direction associated with this graph. Okay. In the Prim's algorithm, our goal is to find out the minimum spanning tree. Okay. And in this graph, there is a S, okay, in which a weight is associated with every edge. Okay. So in the Prim's algorithm, first we select a random vertex, randomly select any vertex. After that, we cover all the adjacent vertices by selecting the minimum edge. Then we will find out all the edges that connect to that tree with the new vertices. And in each round, we select a minimum edge and add it in the tree. Okay. So first, we select a edge. Suppose we have choose a vertex in the above graph. We choose a B. We are selecting a edge, that is your B. Suppose we are selecting an S, that is your B. We selected this S. Suppose we have selected as B at first. this edge. Okay, first we have selected a vertex, that is B. Now we have to select the shortest edge from B. What is the shortest edge from B? There are two edges which are connected from it, that is B to C, that is 10. The weight is 10. The cost of this edge is 10. And there is one more edge that is connected to D, and the weight of this edge is 4. And the cost of this edge is 4. Okay. Then we will find out the minimum weight, minimum cost. The minimum cost is 4. In 4 and 10, the minimum cost is 4. So the SBD, that have your minimum weight. So we add this as B to D in the MST. So we connect B to D in the MST. In the first step, this is connected, this is now selected in the first S in the graph, that is minimum spanning tree in for 2. Now again we will select the S with minimum weight among all the others. Now we will select next minimum. We have now 2 edges, B and D, B and D. Now we will select next minimum in among those. There is one edge connected with B, and the cost of this edge is 10. This is 10. And there are 2 edges that are connected in D, that is D to C, that cost is 2, and D to E, the cost is 1. Then we will select the minimum weight is the minimum weight, minimum cost, the minimum weight among all the other edges. We have 3 edges, first, second, and third. Then we will select the edge which have minimum cost. So the edge D to E, that have your minimum cost. So we will add this edge in our minimum spanning tree, that is D to E. And the cost is your 1. Okay, first we have select one source node, that's it your B. From B we have find out a minimum weighted edge, that is your B to D. We have added this edge in our minimum spanning tree B to D. Now from among all the edges associated with B to D, we have find out one edge that have your minimum weight, that is your D to E, because the weight of this edge is 1. Now we have added this edge in our minimum spanning tree. Okay, next we will select another edge among all the edges which have minimum cost. Now we have one more edge added, that is E to C, and the cost is your 6. The 4, this is also covered, 1 is also covered. Now we have also 3 edges, B to C, the cost is 10, D to C, the cost is 2, and E to C, the cost is 6. Now we will select one edge among all 3 edges with minimum cost. So minimum cost is your 2, and the minimum cost is your 2. Now we will select another as D to C. D to C, the cost is now 2. Okay, we have selected one more as with minimum cost, that is D to C, and we have added in our MST minimum spanning tree, and the cost is now 2. Now we have covered 4 the vertices in which the cost associated with each edge, that is your minimum. Okay, now there is only one vertex, one node is left. in the graph. That is your A. That is your A. And we will find out the minimum cost edge that is connecting through it. But there is only one edge, that is C2A. Now we will add this edge in our MST. That is your C2A. C2A. And the cost of this edge is 3. Okay. So total cost will be, what will be the total cost? Total cost will be 4 plus 2 plus 1 plus 3. So the total cost of this Prim's algorithm to cover all the vertices is your 10 unit. So in the graph, you can see that with the help of these edges, we are traversing all the vertices of the graph. And the cost of all the edges, that is minimum, that is 10 unit of time. So this is called your minimum spanning tree. So with the help of Prim's algorithm, we have find out the minimum spanning tree. Minimum spanning tree is the spanning tree in which the overall cost of that subgraph of that spanning tree, that should be your minimum, then that tree is called your minimum spanning tree. Okay, is it clear, or should I explain again?
No, sir, it's clear.
Is it clear? Okay, so in the Prim's algorithm, we have find out a minimum spanning tree that have covered your all the edges, all the that is cover your all the vertices. Okay, and the cost was minimum in this example. Okay, the cost was your 10 unit time. Okay.
Sir, I have one question.
Okay.
Is it differ
Okay.
in directed graph or not?
Okay. Tell me, what is your question?
It differ in directed graph or not?
This is an undirected graph. Okay, this is not directed graph. If there is a direction associated with it, okay, suppose there is direction. Suppose there is a direction. Suppose there is simple a direction. This is a direction. Okay. Now the spanning tree will be changed because now this is your directed graph. So okay. Now we will find out a spanning tree. At first, we have selected one graph, one node, that is your B source node. From B, we have two edges to cover two vertices, that is C and D. From B to C, the weight is your 10, and B to D, the weight is your 4. And it is directed because from B, we can also traverse your C as well as we can traverse your D. And the cost is minimum in the 4. So B to D is selected. B to D is selected because it have minimum cost. Next, we will find out next minimum is there are now we will find out next minimum is, okay, we have one is that is B to D. In the directed graph, the age associated with is your 10. 4 is also covered. From D, we have two paths, D to C with two edges, with cost is 2, and D to E, the cost is 1. But from D to E, we cannot traverse because there is no direction from D to C. We cannot cover from D to C, but we can go from D to E. So we will select next minimum among these two from 10 and 11. The minimum is your 1. So we will select D to E and the cost is your 1. Okay. Now we will find out the next minimum. Now we have one as is 10, one as is 2, and one as is 6, and one is 2. The minimum is 2, but we cannot select 2 because there is a no direction from D to C. So we have to select it from this, among this and this. And the next minimum is 6. So we will select E to C. Now we will select E to C, and the cost is 6 in the directed graph. Okay. Now there is only one node left, that is A, and there is only one S that is associated with E, that is C2A, that is the cost of this S is 3. Now the cost is 4 plus 1 plus 6 plus 3, and the cost is 14. Now the cost is your 14 when it is a directed graph. If I have converted this undirected graph with the directed graph by associating some direction with the edges, now I have found out the MST, minimum spanning tree, and now the minimum spanning tree cost is 13. Now is it clear?
Yes, sir, it is clear.
Okay. Then we will discuss about the time complexity, the complexity of Prim's algorithm. Okay. The running time of this Prim's algorithm, okay, depends upon the data structure for the graph and the ordering of the edge. It depends upon your ordering of the edge. Okay. If I use a linear searching in the data structure, I am selecting linear searching for finding the next minimum edge, the next minimum element, the next minimum value. Then the time complexity will be your total number of vertices square. That will be your n square, or in the graph you can also say that v square. Okay, because v is your number of vertices and number of vertices. Okay, that will be your v square. If I am using your binary heap, then the complexity will be your total number of edges into log v, because the height of binary heap, that is your log n. Okay, log v. So the complexity will be your e into log v if I am using binary heap. Okay. So the complexity of Prim's algorithm is your e into log v. The best algorithm is e into log v, where e is your total number of edges and v is our total number of your vertices. Okay. Now we will not discuss that how this log n come. Okay, because we have already discussed how the height of tree is log n, how it is calculated in the first part. Okay, is it clear?
Yes, sir, it is clear.
Okay. Now the next algorithm to find out the minimum spanning tree, that is your Kruskal algorithm. Okay, Kruskal algorithm it also used to find out the minimum spanning tree for a connected weighted graph. Okay, every graph that is also connected. Okay, so Kruskal algorithm is used to find out the minimum spanning tree. Okay, but the steps are different in compared to Prim's algorithms. So the main target of the algorithm is to find out the subset of edges. By using, we can traverse each vertex of the graph. Okay, it also follows your greedy approach. That is your to find out the optimum solution. And every edge in Kruskal algorithm, we will find out a minimum weighted edge every time, because we will in every step we will select first minimum, then we will select next minimum, then we will select next minimum. In every step, in every iteration, we will select among all the edges minimum, minimum, minimum. Okay, so in the Kruskal algorithm, we start from the edges with the lowest weight. Okay, we will not start with any edge of the source. We will select with the edges which have lowest weight in the graph. Okay, and after that we start keep adding the edges until the goal reached. We will first select first minimum, then we will select next minimum, then we will select next minimum, then we will collect all the nodes until we have not covered all the vertex of the graph. Okay, so in this procedure, first we sort all the edges according to their weight, from low weight to high weight, because we are selecting the first minimum, the next minimum, the next minimum. Okay, after that we take a edge from the lowest weight and add that edge in the spanning tree. If there is one condition also, if the edge does not create a cycle, if the edge does not create a cycle, then we will add this edge in the minimum spanning tree. If it is creating a cycle, then we will reject that edge, because if there is a cycle in the spanning tree, then that tree is not a spanning tree. That is not a spanning tree, and that is not a minimum spanning tree. If there is a cycle in the graph, then that is not a spanning tree. We will do this process until we have find out a minimum spanning tree. Okay, with the help of example, I am trying to solve this. Okay, in the computer lab, in the LAN connection, you can use this Kruskal algorithm. Okay, suppose there is a graph, there are different edges. I'm drawing it. I'm drawing a graph. Okay, okay, this is a graph of 5 edges, and the weight is associated with edges. A to B, the edge is the weight of the edge is 1. A to C, that is 7. A to D is 10. A to E, it is 5. B to C, it is 3. And C to D, it is 4. And D to E, it is 2. Okay. First step, we will sort all the edges according to their weighted. Okay, according to the weight, in the ascending order, I will sort all the edges. Okay, if I am sorting the AB will be in the first. Suppose this will be when the is the weight associated is 1 and DE have second minimum weight that is 2 and BC has next minimum weight that is and CD have next minimum that is 4 and AE that have next minimum that is 5, AC have next minimum that is 7 and AD that have next minimum that is your 10. In the first step I have sorted all the edges in the ascending order of their weights in the first step. Now I will select the first edge with minimum cost and I will join it in the MST, in the minimum spanning tree. So the first edge with minimum cost, that is your 1, that is your AB. So I will join this as AB in the minimum spanning tree because it has a minimum weight that is 2. Sorry, that is 1. Okay. Now I will find out the next is with minimum cost, that is your 2 because I have already arranged it in the ascending order, that is DE. Now I have selected one S, that is DE. That is our S, that is our DE. That is D and it is E because it have next minimum cost, that is 2. Okay. Now I will select another, that is BC. I will add this BC as with weight 3 in the minimum spanning tree. If it is not creating any cycle, every time I will check that it is creating cycle or not. BC. This is your BC. BC. We will also check that is there creating on cycle or not. No. Now there is no cycle, so I can select this. Now the next minimum is our CD. Now next minimum is our CD. We will select our next minimum, that is CD. Where is CD? This is CD. It is creating a cycle or not? No, it is not creating a cycle. So I will add it in our minimum spanning tree. Now CD is added here. And the weight associated with this S, that is your 4. Okay, because it is not creating a cycle. After that, we will pick the S AE because it have next minimum, that is A. And we will check that it is creating a cycle or not. AE. Yes, if I am adding AE, if I am creating A, if I am selecting A, after selecting A, you can see that there is a cycle now. There is a complete cycle.
Sorry, sir, I cannot see your screen.
You are not able to see my screen?
Yes, we are visible. It's visible, sir.
Okay. In next step, okay, when we have selected this edge AE, okay, then you can see that now it creates a cycle A to E. So we cannot add this edge. Okay, we cannot add this edge. We will do this procedure until we have not find out any cycle. Okay, after that, when we pick the SA with weight file, including this S, we will create the cycle. So we will simply discard it. Okay. Next, we will select another edge, that is AC. If we are selecting AC with weight 7, okay, I have connected A to C. Now there is also a cycle, so we will simply discard it also. This is also discarded. So this is also discarded because by connecting with AC, there is also a cycle. Next is your AD. Okay. If I am connecting the edge AD with weight 10, there is also a cycle. So simply discard this is also. Simply discard this edge also. Okay. So in the final minimum spanning tree that is obtained from the given weighted graph, from this graph, that is this one, because it covers your all the vertices. It is also covering your A, B, C, D and E with the help of our 4 edges. And the cost associated with this is 1 plus 3, 1 plus 3 plus 4 plus 2, and this cost is your 10. This is your 10. Okay. So in the Kruskal algorithm, the goal of the algorithm is to find out the minimum spanning tree, in which in the every step I have selected a edge with minimum cost, and I have added that edge in the minimum spanning tree. If that edge creates a cycle, I have simply discarded that edge. Otherwise, I have added that is in the minimum spanning tree. And further, we have find out the next minimum is I have added that is in the minimum spanning tree, and I have also checked the condition that by including this as it will create the cycle or not. If it creates a cycle, then I have simply discarded it. Otherwise, I have added it in the minimum spanning tree. I have done this until I have not covered all the node of the graph. If I have covered all the node of the graph, after that, if I add other edges, then I have find out that there edge creates a cycle. So I have simply discarded all the edges. Okay. By sorting these edges in the ascending order of according to their weight, I have find out the minimum spanning tree, the spanning tree with minimum cost. So I have find out the minimum spanning tree in the Kruskal algorithm by selecting a minimum edge in every step. Okay, now is it clear?
Yes, sir.
Okay, this is the Kruskal algorithm. Okay, in the Kruskal algorithm, the time complexity of this algorithm is also your V log V or E log E, because I have used a binary heap in it. Also, if I use sorting algorithms with n square complexity, then the complexity will increase. Okay, but I have used the best sorting algorithms for sorting all the edges in the according to their weight. Then the complexity is our V log V, where V is number of vertices, or you can say E log E, where E is the number of edges. This is your Kruskal algorithm to find out the minimum spanning tree of the graph. Okay. Okay, is it clear?
Yes, it is clear, but sir, which algorithm is best? But all the two have the E log V time complexity. Then why we use two algorithms for that minimum cost spinning tree?
Okay, we both have algorithms. Okay, in both the algorithm we have said that in the first algorithm we have find out one minimum and we have checked so many other options also. Okay, we have traversed, we have the number of comparisons in the first algorithms are more than the number of comparisons in the second one. Okay, in the first one, in the source node, I have traveled, I have compared, I have the number of comparisons so more. Okay, so in terms of number of comparisons, the complexity of prims were higher than in Kruskal, because in the Kruskal the number of comparisons were less. The overall complexity in the Kruskal were less than in the prims algorithm. Okay.
Okay, sir.
Oh, we have one more algorithm, that is your Dijkstra's algorithm. That algorithm is to find out the shortest path from source to vertex. In the prims, I have selected from source to destination one path where I have selected minimum is. In the Kruskal, every time I have selected a next minimum, optimal. Okay, next is our Dijkstra's algorithm. Okay, Dijkstra's algorithm, it is also a graph algorithm that finds the shortest path, shortest path from source to destination, from source to all other vertices. Okay, single source shortest path. But in Primsum Kruskal, we are not talking about source to next destination, source to next part. But in Dijkstra's, we are talking about source vertex to all other vertex in the graph. Okay, it is clear. In Prims and Kruskal, we are checking among only two nodes, but in Zestas, we are finding the shortest path from a source vertex to the all other vertices in the all in the nodes of the graph. That is single source shortest path. There is only one source, and I will cover all the vertices, all the nodes with minimum cost. So it is a type of a greedy algorithm that only works on weighted graph. And there is one constraint there in the discharge algorithm, that there must be a positive weights, weighted graph and positive weights. Okay. So the basic concept of the discharge algorithm is it begins at the node of the source node. From the source node, it examines the graph to find the shortest path between that node and all the other nodes in the graph. For example, you are traveling from one city to other city. You open your Google Map. Okay, with the help of Google Map, you find out that which is the shortest path from one city to other city, and which is the shortest distance from among nodes. So Google Map is the best example of this Dijkstra's algorithm, or best application of the Dijkstra's algorithm, which use our uh, Google Map. Okay, with the help of example, we will try to explain it. So okay, I'm sharing a screen. Is it visible? I think Okay, not visible. Okay.
No, no, sir.
Okay. Trying connect. I think now it is visible. Is it visible?
Yes, sir.
Yes.
Okay. This is a graph. This is a weighted graph in which we have 6 vertex, 6 nodes. Okay. And the goal of the algorithm is to find out the single source shortest path. I have selected node 1 as a source node. Okay. Now we will find out the single source shortest path from source to vertex. Okay. In this algorithm, at first we select the source node. After selecting the source node, we examine the graph to find the shortest path between that node and all the other nodes in the graph. Okay. And every time the algorithm keeps records of the presently visited shortest distance from each node to the source node. Okay. Then it will move to the next step. Okay. Initially, the source node is our 1, and these are our destinations 2, 3, 4, 5, 6. Because this is a single source shortest path. From the source 1, we will cover all the other nodes, all the destinations. In this algorithm, at first, we mark the distance of source node from 1 to 1, that is our 0, because 1 to 1, that is our 0, from same node to same node, and we set all the other nodes to infinity. Okay, in the initial state, the source to source, the cost is 0, and in all the other nodes, we assume that the cost of traveling from source to destination, that is infinite, that is infinity. That is infinity in all the destination from source to destination. Okay. Then we will then set the unvisited node with the current smallest distance at the current node. Okay. The current source node is 1. Now we will go to the next unvisited node with minimum cost, with their smallest current distance. Okay. From source 1, I can move either our node 2, node 3, or node 6. Okay. From node 1, the cost of traveling 1 to 2, that is 7. I will put 7 here. In the infinity and 7, minimum is 7. So I will put 7 here. I will mark 7 here. And from 1 to 3, initially the cost is infinity, and the next cost is 9. I will compare both 9 and infinity. The minimum cost is 9, so I will put 9 here. And 4, destination 4, it's not possible to visit from 1 to from node 1 from source, so I will put infinite here. Okay. Node 5, it is also not possible to visit 5, so infinite also here. And 1 to 6, the cost is 14. I will put 14 here in the first step. Okay. Then I will select the minimum node. I will check the minimum cost among all 7 destinations, in all the 5 destinations. And the minimum value is our 7. The minimum value is 7. So I will put this 7, the cost of this, that is the destination, is 2. So I will put this node in my source now, because I have covered this destination 2 already. Now I have moved from 1 to 2. Okay. Now I will check 7 is also covered. I have put 7 as it is. Now 2 to 3. Okay. There are 2 paths to traverse to 3. That is 2 to 3, the cost is 10. And 1 to 3, the cost is 9. I will select the minimum. The minimum is 9. So I will put 9 here. Then 4. Yes, now it is possible to visit 4 from 2. So the cost will be 7 plus 15, because the cost is 7 plus 15, because we are finding the shortest path from source, and our source is 1. So the shortest path is 7 plus 15. Okay, first one, that is our 22. In the first step, if there will be another cost, then it will be removed. Okay, and 1 to 5, 1 out to 5, it is not possible to visit, so it will be infinite also. And 6 is here. Now we will check that the one cost is our 14. The cost is now here is 14. Okay, there is one more path from traveling 1 to 6, that is 1 to 6. No, there is only one path, 1 to. Okay, by traversing with these 2 source nodes, there is only one path, 1 to 14. 1 to 6, that is our 14. Okay, so the value will be 14 here also. Okay, now I will select the next minimum. Next minimum is 9. 7 is also covered. Next is 9. That is our destination 3. So I have put, now 1 is also covered, 2 is also covered, and 3 is also traversed. Okay, now I will check. Next, 7 is also covered, 9 is also covered. Now check that. 4, node 4. Node 4, the cost is 7 plus 15, that is our 22. And there is one more path for traversing 1 to 4, that is 1 to 3 and 3 to 4. And the cost of this path is 9 plus 11, that is 20. Now I will compare 20 and 22. Which are minimum? That is 20. So the 22 will be replaced by 20. Now the new path will be 1 to 3 and 3 to 4 for traversing the 4. Okay. Next is next is 5. It is possible to visit 5 with the help of 1, 2, and 3. 1, 2, and 3. No, it is not possible. So it is also infinite. And 1 to 6. 1 to 6, one path is 1 to 6, that is 14. And there now there is one more path, that is 1 to 3 and 3 to 6. That is 9 plus 2, 11. Okay. 11 and 14, which was the minimum? 11 is minimum. So this 14 is now replaced with 11. Okay. Now I will select next minimum in these three. The next minimum is 11 and the node is 6. So I have also traversed 1, 2, 3 and 6. Okay. Now we have only two vertex, that is 4 and 5. Node 2, that is also covered. 9, that is also covered. 11, that is also traversed. Now we have one node, that is 4. That is 4. Now I will also check, is there any shortest path from A to 4? From 1 to 4, there is any other shortest path? Here, the minimum cost is 20. By traveling from 1 to 3 and 3 to 4, the cost is 20. By traveling 1 to 2 and 2 to 4, the cost is 22. If there any other path? No, there is not any other path. So I will select this 20. Next, 5. Is there any path from 1 to 5? Yeah, by covering 6, I have one path. Now the path is 1 to 3, 3 to 6, and 6 to 5. I have covered 1 to 3, 3 to 6, and 6 to 5. And the cost is 9 plus 2 plus 9. That is 20. So now the cost is 20. Now you can see that 4 and 5 both have same value. The cost is same. So you can traverse either of them. Suppose I have selected 4 as a node, as a destination. 1, 2, 3, 6, and 4. Now 4 is selected. Okay. So 4 is selected. Say 1 is already covered. 9 is already covered. Now 20 is covered also. 11 is also covered. Now there is only one left, that is 5. Is there any other route from traveling 1 to 5? Yes. Now there is one more route, that is 1 to 2, 2 to 4, and 4 to 5. And the weight is 7 plus 15 plus 6. That is 28. And the path 1 to 3, 3 to 6, and 5, the cost is 20. Which was his minimum? This is our minimum. 20 is the minimum. So I will select 1 to 3, 3 to 6, and 6 to 5. Now 1 to 3, 3 to 6, 6 to 4, and then 5. I have selected this path. Now I have covered this path. Okay. Now you can see that I have traversed all the nodes in the graph. I have traversed all the nodes in the graph with the minimum cost, from source to destination. From source to destination, I have covered all the path. You can see that from 1, with the minimum cost, I have moved to 2 with the cost 7. Then next, I have moved to 3 with the cost of 9, that is 1, 2, 3. That is the cost is 9. Next minimum is 11, and it is covered with the help of 1, 3, and 6. With the help of 1, 3, and 6. And the cost is 11, because you can see that now the cost is 11 and the cost is 9 plus 2, 11 here. Okay. Next, I have visited after 6, I have visited 4 with the cost of 20. with the cost of 20, 11 plus 9, with the 11 plus 9, with the cost of 20, I have visited 4 also, and with the cost of 20, I have visited 5 also. 9 plus 9 plus, sorry, it is 2, not 11, it is 2. It is 2, 9 plus 2, 11. With the 20, I have also visited 5. Here is the 5. And the cost associated with this is 9. And the total cost is 9 plus 2 plus 9. That is our 20. So, with the help of discussed algorithm from source to destinations from all the other nodes, for source 2 is also destination, 3 is also destination, 4 is also, 6 and 5. From source I have traveled all the destination with the path. With the shortest path, I have covered all the destinations from source to destination. So, in the Dijkstra's algorithm, at first we select the node, the source node, and it examines the graph to find the shortest path between the source source node to all the other nodes of the graph. Okay, in Primsum and Kruskal we have find out spanning tree, but in Dijkstra's algorithm we have find out the shortest path from source node to all the other destination path as your Google map. So the algorithm keeps records of the presently visited shortest distance from each node to the source node, and it updates all the values on the basis of minimum cost of the shortest path. Okay, once the algorithm has been retrieved the shortest path from source to the destination, the node is now marked as visited. The node is marked as visited, and we have included that path in this graph. Okay, so this procedure continues until all the nodes in the graph have been included in the path. All the nodes, until all the nodes are not covered. So in this manner, we have path connecting to the source node to the all other nodes with the minimum cost, to find out the shortest possible path to reach each of the node. Okay, so the time complexity of this algorithm is E log V. The time complexity is E log V. Is it clear?
Yes, sir.
Yes, sir, it's clear.
Okay, so in the Prims and Kruskal, we have find out the minimum spanning tree, and we have checked between only 2 nodes. But in Dijkstra's algorithm, we have find out the single source shortest path from source to all the other algorithms. Okay. Okay. It is clear. So Prim's algorithm is more efficient when there is a dense graph. Okay. And Kruskal algorithm is good when there is a sparse graph. Okay. If there is a dense graph, then Prim's is best. Okay. If there is a scattered sparse graph, then you can say the Kruskal will perform best, because every time it will select minimum. Or if there is a more dense graph, then Prim's algorithm is best, because Okay. And in the discuss task algorithm, we have find out the shortest path. I think these three algorithms are enough for today. Okay.
Okay,
Yes,
sir.
Okay. In the next class, we will discuss some more techniques. I think that will be your DFS, BFS that you already know. Okay. Then we will discuss some new techniques. Okay, class.
Okay, sir.
Okay, sir.
Your presentation on the group as well.
Sir, I have one question.
Okay. Okay.
That we said in greedy technique, we
Okay.
find an every step minimum value, and then the result may be minimal or not. We study three algorithm. The result also generated the minimum value. Why we say in the definition of the greedy techniques
Hmm.
that the result may be optimal or not.
You are talking about today's or algorithms or previous?
No, sir, the techniques, the greedy techniques, when we define the greedy techniques, we
Okay.
say in every step we select the minimal and the result may be minimal or not. And these three algorithm, we said that we saw the result is also the minimal,
Oh,
optimal.
uh, in first two algorithm, in prim and Kruskal algorithm, okay, you have find out the minimum cost because we are hoping that we are finding out the minimum spanning tree. As the definition suggests, what is minimum spanning tree? Minimum spanning tree is that spanning tree which have minimum cost. Which have minimum cost? Which if all nodes have minimum values, then the cost of that spanning tree will be minimum. And if I've used directed graph, then you have checked that now the cost is not minimum. The overall cost is now not minimum because I have used the directed graph. Now I have not selected every time the minimum. Okay, every time you cannot say
Okay,
that
sir.
every time it is minimum. If I have used the directed graph, then you have checked that the minimum cost is 14. And for the same graph, the minimum cost is 14. And for the same graph, if I have not used that graph was undirected, the minimum cost is 10. Okay, but in the disasters, we are not talking about the minimum cost between two nodes. We are talking about the overall distance from source to destination. If you will find out the MST for the disaster algorithm graphs, then the output will be different. Okay, because I'm checking the cost from source to destinations, not among those two. Is it clear?
Okay, it's clear, sir.
Okay, okay. Is there any questions?
Thank you, sir.
Okay, class, we will meet soon. Okay, enjoy your day. Okay, class, if there is no questions, you may leave. Okay, thank you.
Thank you, sir.
Thank you, sir.